Hello students, welcome back. Nice to see you. Let us start with the next module of the chapter rotational motion called as the angular momentum of a rotating body. Now students, in this module we are going to derive an expression for the angular momentum of a rotating body. So let's move on to the module students. For this, let me consider a rigid body. This rigid body is rotating about an axis x, O, x dash in the anti-clockwise direction. Now students, this axis x, O, x dash is perpendicular to the plane of rotation. We all know that this rigid body is made up of n number of particles, but to keep things simple, let me consider three particles. The first particle which is of mass m1, the second particle which is of mass m2, and the nth particle which is of mass mn. Now students, the first particle is at a distance of r1 from the axis of rotation, the second particle is at a distance of r2 from the axis of rotation, and the nth particle is at a distance of rn from the axis of rotation. Now students, we all know this. When this rigid body rotates, the particles of the rigid body move in a circle, and all these particles will have the same angular velocity. Now, even though they have the same angular velocity, the linear velocities of all these particles are different. Why it is different? You see that students, the radii of the circular path traced by all the particles are different, and hence all these particles will have different linear velocities. So let V1, V2 and Vn be the linear velocities of the first particle, the second particle and the nth particle. Now students, we all know the formula for linear momentum. What is linear momentum? Oh yes, linear momentum is given as mass into velocity. So what I'm going to do here is, I'm going to find out the linear momentum of the first particle, the second particle and the nth particle. We can write the linear momentum of the first particle as m1 v1, similarly the second particle as m2 v2 and the nth particle as mn vn. Now students, we need to calculate the linear velocities. For linear velocities, which formula to use? Circular motion. Have you studied this formula? Oh yes, v is equal to r omega. So we can say the linear velocity of the first particle is r1 omega, the second particle is r2 omega and the nth particle is rn omega. So then the linear momentum of the first particle will become m1 r1 omega, second particle m2 r2 omega and the nth particle will become mn rn omega. Now students, we all know the formula for angular momentum. Oh yes, angular momentum is linear momentum into perpendicular distance. So the angular momentum of the first particle can be written as L1 equals to P1 into perpendicular distance. Now, you see the first particle. What is the perpendicular distance of the first particle? There you go. It is R1. Now remember students, the perpendicular distance is always measured from the axis of rotation. So we can say L1 is equal to P1 into R1. Similarly, L2 is equal to P2 into what is the perpendicular distance of the second particle? Oh yes, there you go. It is R2. So we can write L2 is equal to P2 into R2. Similarly, Ln is nothing but Pn into what is the perpendicular distance of the nth particle? Oh yes, there you go. It is Rn. So Ln is equal to Pn into Rn. Now students, we all know the linear momentum of the first particle, the second particle and the nth particle. So we can just substitute the values of the linear momentum into the expression of angular momentum. So what we will get? We will get the angular momentum of the first particle as m1 r1 square omega, the second particle as m2 r2 square omega and the nth particle as mn rn square omega. Now students, angular momentum is a vector quantity. Now all these particles are moving in the anti-clockwise direction. So we can say that the angular momentum of all these particles are in the same direction. That is, all these particles will have the angular momentum along the axis of rotation. So then we can conclude the total angular momentum of all the particles is nothing but L1 plus L2 plus so on till Ln. Now students, we have the angular momentum of the first particle, the second particle and the nth particle. So we can write L total as m1 r1 square omega plus m2 r2 square omega plus so on till mn rn square omega. Now students, this expression can be written as L total equals to, now hold on, you see there is a term common. Which term? Oh yes, omega is common. So I can pull out omega, within bracket I will get m1 r1 square plus m2 r2 square plus so on till mn rn square. Now students, this expression can be written as L total equals to, now this term within the bracket m1 r1 square plus m2 r2 square plus mn rn square can be written as summation of I is equal to 1 to n mi ri square into omega. Now students, this rigid body is made up of the n number of particles. So we can say the total angular momentum of all these particles is nothing but the rotational angular momentum of this rigid body. Now why? Because this rigid body is made up of these n number of particles. So L total will become L rotational. L rotational is equal to, now this term summation of I is equal to 1 to n mi ri square is nothing but moment of inertia. So L rotational is I omega. Now students, this is the expression for the angular momentum of a rotating rigid body. I hope so. You've understood this very clearly. Thank you. Rise and shine.